of light as human beings. Okay? Where is more signal available? Or where do we want more signal to be available? In the low light. Because when we are integrating, remember when we have integrated, in the low light we have less signal. In the bright light we have a good amount of signal. So in low light, if we do logarithmic compression, I get even less signal. So from a good pixel point of view, in the low light, I should expect a linear response. A linear response will be better for me. So the pixel gives me a linear response in low light, but a logarithmic response in high light, which is kind of good. It ticks both the boxes. Can somebody tell me problems with this design? So one problem, of course, is I'm still making my transistors from the smallest size possible, which means I will have fixed pattern noise. I will have mismatch. Now I'm adding a new type of mismatch. My pixel moves from linear to logarithmic. The point at which it moves from linear to logarithmic will also vary from pixel to pixel. Okay? There's a slightly bigger problem here. And the problem is not just from these pixels. The problem is also from the human visual system. At the beginning, I said we do some form of logarithmic compression in our human eye. It's Stevens power law compression. At the same time, yesterday we talked about color. And we said color we get by red plus blue plus green. How do we get color when we have got log of red, log of blue, and log of green? We get color by linearly mixing individual colors. If my individual signal is the logarithmic of that, how do we produce color? Do we do anti-log, then add and then do log again to get color? For doing anti-log, as we discussed, is a noisy operation. Which then leads to the question, how does the brain do it? We know human eye does logarithmic compression of input signal. So how do we see color from that log signal? When you find the answer to that question, send an email to the Nobel Prize Committee. It's still poorly understood at best. You can essentially do log R plus log B plus log green for small signals, because for small signals, log of x is equivalent to x. But for bright signal, the same relationship does not always remain true. Okay, let's do one more question from our pixel diagram. The other pixel which I discussed the other day was this pixel. So this was another patented pixel of ours, which basically has a comparator inside each pixel. Remember we talked about this idea wherein why don't we feed a reference signal to the pixel and put that comparison as a metric of the signal input. Now comparators can be very large. So I designed a comparator saying why can't we use a single transistor as a comparator? Not a great comparator, it's not a brilliant comparator, but it kind of works. Think of it this way. If this voltage is low to start with, and this voltage is high too, so this is the voltage which is there due to pixel being reset. Okay? So gate voltage is high, this voltage is low, this transistor is on. Right? So whatever appears here will kind of appear here as well. It's an on transistor. Good. So at this voltage is now falling down and this voltage is going up. So at some point of time, my VGS will become negative. This transistor will switch off. At that point of time, whatever is held here is held on these capacitors. There's no place for that charge to go away. While this voltage keeps on going down, this transistor is off. Whatever was here is being held on this capacitive node. Now your task would be to find a relationship between these output voltage and the input photocurrent. How will we go about doing this? At this point, you guys are saying, you are asking the question, you are solving them. Why don't you solve this one as well? So I'll give you a hint, but I really expect some of you to try this on. So this signal is going down. What is the relationship here? We can map it as a linear function, right? A minus B of photo current. This signal is going up, which is another similar relationship. So how do you find the point at which they interact? So how do you find, when there are two waveforms which are going up, how do you find the point at which they will cross one another? So let's give you two functions, a1 plus bx and a2 minus bx or bt. Okay. Now let me tell you precisely the problem here. Oh, for heaven's sake! The function which is falling down is sum a minus b times I photo times t. Okay, or you could have said I photo times c PD. Okay, so there is photocurrent and time there. The other function which is going up, my reference function, this is my V node Ni. My reference function is going to be sum A ref plus B ref times time. There's only time here. It's just going up with time. There is no photocurrent here. At some point, they cross. That crossing point I will get a certain voltage. I need to know that voltage as a function of I photo. There should be no time involved anymore, because once they have crossed at the same time. Okay? So my output function, which I am keeping it same, so once they cross, I keep it same. That should become a function of my photocurrent. That's what I want you guys to find out. And then we'll make it more complex to see, can I get a logarithmic response out of it? Tell me, how would you go about doing it? Even if you don't want to do it right now, tell me, how would you go about doing it? Is the question clear? For those of you who are still thinking, think what happens at the time they cross. What is common between these two signals? Time. Well done. So we write these two equations in form of the time and equate those two. Done. Okay? So can somebody give me a quick relationship between V out and I photo? For this one, I'm going to wait. So this is the comparatively easier problem. Well, we'll come to the harder problem in a minute. Yes? Okay, the more longer we wait, the longer the coffee break will get, right? Ah, sorry. I can give you the solution which I just showed you on the screen. But ideally, the problem should be fairly straightforward. If you find time from the first function, which will be Vni minus Ai minus Vni multiplied by C divided by I photo. If you find the time from the second function, which is Vref minus Ar divided by Br, equate the two timings, you will get a response function which will have Vref as well as your V output. Okay? Or you'll get a time at which these two will be common, and then you put the time back in this equation, you'll get a V output equation. Now that's a comparatively simpler problem. The harder problem is, I said I can get any monolithically increasing function from this one. If my customer then comes and says, you know what, I don't want a linear, you can see this will be a linear response. Two linear functions meeting one another, I'll get a linear output. I want a logarithmic output. So I know what kind of output I want. How do I go back and derive the reference function which is needed? That actually cannot be derived. There is no mathematical closed form solution to that problem. Actually, I can show it to you how it looks like. Oh, what are you doing? What you end up getting is a formula not between the reference function as a function of time, but what you end up getting time as a function of the reference value. So what I would have liked is how does my Vref changes with time? But inverting this function is quite challenging. As you can see, we have Vref here and we have Vref also in 10 to the power, or right? So inverting that function becomes very challenging. But that's not a problem, because essentially what you are saying is V is a function of time. I don't know that, but I know time as a function of voltage. I can still plot that value. Okay? Good. This problem again we did last time when we tried doing a speed of ADC required for a camera. When you make smaller cameras, we don't try to have one ADC per column, particularly when you're making things like cameras for endoscopes, wherein you know you're not going to get very high pixels, so the camera has to be very small, as small as possible. Right, we have been talking for about an hour. I said I will give you a break after an hour, so let's take a break of 10-15 minutes, and then we'll come back to continue our micro electromechanical systems work. And we'll go to lab in the afternoon. Tomorrow we'll revisit camera pixels and we'll do a bit more advanced pixels. Till now we are only going through the simpler pixels. We'll go more advanced designs of these. Okay? Having said that, whatever you have learned till now, that actually is enough to make a camera in industry. And most of the pixels which are in the market are very similar to, or if not exactly the same pixels which we have taught to you till now. So if you can do a 40 pixels, you can write in your CV from here onwards that experience camera design. Good. We'll stop now and we'll meet in 15 minutes from now. Okay? Thank you. Okay. Can you hear me now? Okay. You can make these clamped at the two beams and the resonators could be going up and down in the torsional mode. The mode of equations remain fairly same. Let's analyze one of these in a bit more detail. Now, out of plane motion is easy to understand. Essentially, you are seeing something going in and out of plane, but it's slightly difficult to excite and measure. The way to excite a number of large excitation is basically you take a resonator chip, put it on a piezo transducer and then shake the whole chair. If you shake the whole thing, they start moving on their own. The one which is slightly easier to appreciate for early analysis would be the in-plane motion. Things are moving. So we have got a plane, I have built a resonator, and the resonator is moving in the same plane as my substrate. Okay. A very simple way to excite this electrically would be something of this sort. You make a spring, you make a free mass. I hear a noise. Do you hear a noise? This is electrical engineer's problem. We can't live with noise, right? Okay. And then if you have a fixed electrode, if you just apply a voltage between these two, what will happen? So that's metal, there's a spring here. If I apply a voltage on this node, what will happen here? There will be electrostatic pull. This looks like a capacitor, right? Two metal plates. If one metal plate is free and the other has got charge, what will it do? There will be electrostatic force trying to pull it towards itself. Right? Two charge have got electrostatic. The first law of electrical engineering you might have read about is charge divided by square of the distance is proportional to that. Okay. So this electrode will try to pull this electrode towards itself. That looks like your excitation force. Now, as it tries to get this side, the spring will try to have the restorative force. It will try to pull it back. And now you can see why this thing will oscillate in between. Okay. If we apply this electrostatic force, if it's a purely DC force, it will be entirely pulled in due course of time. If it's an AC force, a sinusoidal AC force, the moving mass will move up and down. Okay? And the amplitude of this mass will then depend on if the applied sinusoidal force has got the same frequency as the resonance frequency of the system. Now, electrostatic force is a kind of weak force. It's not a very strong force, right, compared to other mechanical forces. So often a single parallel plate finds it very difficult to provide enough excitation, particularly when we are making small resonators. Remember, our parallel plates, everything is being quite small. So we often do these interdigitated finger-like structures where we are increasing the force of excitation and increasing the total force by having large number of such fingers. Okay. The principle of operation remains the same. You have got electrostatic pull between the resonators and it's going up and down. So here is an example of my postdoctoral work. It's a very large scale resonator. So you can see these the MEMS was also very noisy. It made my life miserable when I was working with it. So it has got 4 large bond pads in between. This is to connect electrical signal to it. The reason why I like it, I can electrically excite it and electrically measure it as well. And we'll show you how I can electrically excite it and measure it. Now, the way it is designed, I think I should stand up and have a talk. The way it's designed is these are the springs here on the 4 corners. Okay? And then we have a moving mass which is all around this structure. And you can see there are these sawtooth forms, right? So there is, if you look, there is one sawtooth here with loads of fingers coming out. That is the still part. Anything connected to the bond pad is the still part. It's not moving. On the other side, there is another sawtooth part which is connected to this mass which is going all around. Okay? It's a bit tricky. And here we have got more of these sawtooth fingers. So everything connected to the bond pad. So from each bond pad, I have got a line coming out which is connected to one side of the sawtooth, another line coming out, and the other side I have got this line which is freely moving. So many sawtooth waveforms we did only to increase the number of the amount of electrostatic force. Here each one of these about 2 micrometer in dimension, and they were made in Kinetic Foundry in UK, and the gap is of the order of about a micrometer. Okay? The idea is as we apply electrostatic force from 2 of these, this whole structure starts moving. Okay? So I apply 2 of these to apply an electrostatic force, but then I use another 2 of these to measure by how much is it moving. Okay? And we'll see in a second how do we measure this structure. Now, fairly large resonator, the overall size is roughly 100 micrometer by 100 micrometer, whereas each individual resonator is just a few micrometer by about 2 microns. Okay? Good. Now, then comes the next question, which is how do we talk to resonators? By talking to resonators, we mean how do we excite it and how do we measure it? The excitation of resonators can be through one of many different forces which are there in nature. We could do electrostatic excitation. I just saw an example of this is an example of an electrostatic excitation. We could make the resonators to be of magnetic material, and we can use a magnetic force to excite. Piezo is shaking the whole thing. We could do a thermal excitation as well, apply heat to it to start moving. And then comes the measurement part. If something is moving, you can always do an optical measurement, right? You can see that, you can visualize it, you can take a picture of it. But if it's moving at a very high speed, a megahertz, then taking pictures is slightly tricky, particularly when the structures themselves are fairly small. In such systems, we use some sort of laser Doppler velocimeter. So in the sense, we shine a laser light on it and then look how what's the time it takes for the laser beam to go there and come back. And we measure velocity using a laser beam. The problem of optical measurement is you need an external device to measure this tiny device. You need a laser source and all of these things to measure. So they're very tricky to integrate. At the end of the day, we want a small scale system which we can sell into the market, not necessarily a system with which you need to buy an instrumentation as well. Just the way we could excite something magnetically, we could also measure it magnetically. If there is a magnetic flux changing in the field, you can, it could become a transformer-like thing. Okay. We could also do resistive measurement if the resistance of the things are changing. And I will show you an example of this. So, thin films, when you stretch them, their resistance changes. So if things are moving up and down, the resistance is changing. So we just measure the resistance change in these materials, and that gives us an idea of the motion which is happening. Now to give you an example how this circuit worked, remember the big resonator which I showed you earlier. So what we had a moving structure which is all around, and plus has got all these interdistant fingers. And that structure we have grounded. So electrically, it looks like this grounded moving structure, which is moving between parallel plates. Then two of these plates we are using for excitation. So we basically apply a force here. Okay? And we are applying a DC force plus and minus an AC force. Okay? So on one plate we have got Vd plus Va, on the other plate we have Vd minus Va. On the other plate, we are looking for its motion. So essentially, it looks like a big plate. From one side, we are exciting. On the other side, we are measuring how much it is moving by. Okay? Because that will tell us how far we are from the resonance frequency. And then the rest of the circuit is fairly simple. So what happens? What's the? Oh, you guys are getting a slip. Whatever that means. Huh? Food coupons. I never don't get food coupons. That's not nice. All I have to eat is this mirchi bhaji, chili bhaji. They're not even doing any work. Okay. What's the current in a capacitor? So that's a capacitor, right? Essentially, you can see there are two capacitors, the moving plate and the fixed plate, and the moving plate and the fixed plate. Let's try to understand how it works. What's the current in a capacitor? C dV dt. Now that's an answer you give when you have been an electrical engineer for 4 or 5 years, which most of you have been, right? You have passed your bachelor's, so you have forgotten the fundamental question. If you ask a first-year electrical engineer or first-year engineer, what's the answer they give? What's the current in a capacitor? You had assumed the capacitance is constant. Yes? As my middle plate is moving, what is changing? The capacitance is changing. Now look at this circuit here. This is an op-amp, right? OTA. If I apply a V positive on the positive end, by virtual ground, I will get the same voltage here. So the voltage applied is V0 here and another V0 here. So DC voltage is fixed in the readout side. So let's again ask the question, what's the current in a capacitor? How do we get that C dV by dt equation? CV is the charge in a capacitor. And we say dq by dt is current, so we say C dV dt. But the actual relationship of current in a capacitor is C dV dt plus V dc dt. Are you with me? Or do you want to do it on the board? Right? So here we are doing the other way around. We are keeping the voltage same, and we are measuring as this thing moves up and down, what happens to the capacitance between this plate and this plate? That changes, right? And the relationship of that change will be? It's a parallel plate capacitor. What's its capacitance? Epsilon naught, epsilon r Area divided by distance. So as my distance is going up, my capacitance, when my distance becomes smaller, my capacitance goes up, and vice versa. But there lies a problem. It's a non-linear relationship because the distance is in the denominator. Right? So it's not that the distance changes by 1 micrometer, my capacitance is also changing by 1 unit. Agreed? Okay. In this case, it changes by 1, but if it changes by 2, my capacitance changes by 1 by 2. Okay? So it's not a linear function of distance. But as you will see, by doing a positive and a negative biased excitation, I kind of get a linear function of that movement. So the current produced here will be V, voltage which I have applied is V naught, times change in capacitance with time. That current essentially passes through a resistance here, and I get a voltage on both sides. I then take the difference of these two voltages through an instrumentation amplifier. So rest of the circuit is fairly simple. Okay. Let's look at the excitation side. What happens here? How does this thing move? So I'm applying a DC voltage. I will need a minimum DC voltage to let the thing move, and then I am applying a sinusoidal, small sinusoidal voltage. Okay. If my small sinusoidal voltage is having the same resonance frequency as the system, this will start moving up and down with a more magnitude. Now, it's not always the case that will move by itself. What stops things from moving? There's a Newton's law which basically says nothing moves on its own. Okay? But in real life, we get something else stopping things from moving. Well, sorry. If I push something, it doesn't want to move. What is stopping it from? What is stopping this from moving? Sorry? Gravity is in this direction. I'm moving it in this direction. So gravity and mass will be related. Mass causes the weight. Okay? But weight is in this direction. If I'm applying a force exactly 90-degree opposite to it, what stops things from moving? Or think of it the other way around. Something is moving. What is trying to stop it? A car is moving on the road. What tries to stop it? One is the road friction, right? What is the other thing which is trying to stop the car from moving? Air. Well done. Which is the bigger force on a car? Is it the road friction or the air? Road friction? Agreed? Okay. In the second half, remind me, we will do a tutorial on the forces on a car. Okay? And then we will try to calculate which one is the bigger. So, road friction, what is it dependent on? Mass, right? Road friction is dependent on the weight. Whatever weight is applied, it's a something multiple of that. And we put, but cars have got a very unique thing. They are not a solid rigid structure. The things which are moving are circular. It's the tires, right? And they have quite a low friction coefficient. Whereas what is facing the air? The whole front of the car. So you will realize when we do the maths, till a certain velocity, which is fairly low velocity, is the road friction which causes the problem. But after that, it's the air which is a bigger problem. Why do you think we make cars in aerodynamic shape? They are made in a something like an arrow kind of shape, right? It looks like this. Or even your high-speed trains, what's the name of the high-speed train in India? Vande Bharat or Namo Bharat. They all have got a frontal design like this, right? If it was a road friction, why do they have this design in the front shape? And who gives the drag force? Air, right? So essentially what you're trying to do is you're trying to minimize the surface area which is in touch with the air. This is why, missiles or bows which are diagonal, they go faster. Thrice throwing something of the same mass which has got a flat shape. Right? Or you have played frisbee, right? You've tried, or you try throwing a plate, food plate, on its edge side versus its front side. Which one will go further? The edge side. Why does it go? A surface area to the air is limited here, right? So the viscous drag which the air is putting on it is low. So we just realized air is a bad thing. We all agree air is a bad thing? We also breathe the same air, or else we'll not be a human being if there is no air on us, right? But for motion, air is a bad thing. We'll come back to this in a few seconds. So that was an example of electrostatic excitation and electrostatic readout. Here is an example of resistive readout. So these are piezo excited. So this is a graphene resonator which have got 4 bond pads on the 4 sides. And this looks like an H beam. So on the 4 sides it is held. And as we shake the whole thing, the resonator starts going up and down. And as it goes up, essentially it goes like this. The upper layer is stretched and the lower layer is strained. But this is graphene. It's a one atom thick or few atom thick structure. So as it goes up and down, its resistance changes. So all we are doing is we are measuring the resistance between these 2 plates. And that gives us an idea of the motion. Now, if I measure the resistance, I'm exciting this with, say, a sine omega t, right? 5 sine omega t or a cos omega t. I'm exciting the piezo with an cos omega t. What you would see is that the motion will be on the same frequency at the excitation frequency. And hence the resistance change which I will be measuring will also be on the same frequency as the excitation frequency. So resistance will also be r times cos omega t plus phi, okay, where phi is the phase delay introduced there. Here's another example of a circuit which we made with Professor Deepak Uttam Chandani in Strathclyde University. This is electrically readout. Now I have got 5 such cantilever beams. Why we made 5 we will see shortly. But these are freely hanging, so they're moving up and down. And in this case, we basically applied a laser beam on top on one of these and then looked at how much movement it is taking place. So this is an example of piezo excited, resistively measured or optically measured. Now in 5 slides, I have talked about 5 different ways to excite these things and 5 different ways to measure these things. I have also shown you 5 different types of resonators. Now this is one of the problems why these things don't have market success. Virtually every research laboratory have their own unique design which can only be made in their design process. We discussed the other day, microfabrication is costly. The only way you recover money in microfabrication is if you make a large number of samples or a large number of different devices using the same technology. Here, each technology is only being used for making one type of device. So unless that device has a huge market, despite the fact each device is very good, very highly sensitive, it doesn't make a breakthrough in the market. And that has been a problem with microelectromechanical system or nanoelectromechanical system forever. Chip designers, we make loads of money. Our devices are fixed. We can't do anything with the devices. If tomorrow you go and ask, can you give me a different VT process, the foundry will say, get lost. Design using what we have. 3 different VTs, design it using. Whereas MEMS people, they keep on tinkering with their process to get the optimal response. And the other issue with MEMS is damping. all mechanical devices do not want to move. And when being moved, they want to stop their motion. Okay? We are not in free space. That once I start something, it will keep on moving. All devices which are here there are n number of forces which are acting on it to stop it from moving, air being one of them. And it's just not one sort of damping we have. We have thermal damping, we have acoustic damping, we have n different types of ways in which a device is stopping it from moving. So let's take the example of our resonator which was going up and down. There's air between my my films, right, which is stopping it from moving there. My spring themselves have got some thermal stiffnesses. They don't want to move too much. All of these act as if they're a different quality factor in the system. All of them look like they are, for each resonant system, I have got a dampening system. And many of these damping systems are coming out in parallel. So overall damping looks very much like there are many capacitors in parallel. If you look at the type of damping, you get damping due to one and anything which you are doing. So depending upon the shape and size of your structure, for the same situation, some shapes have got lower damping than others. Depending upon which material have you made it from, which alloy have you made your material from. While making, have you had defects in it? What's the air pressure, what's the temperature, what's the frequency of operation, and how you have gone about making it. All of these lead to some viscous damping or some stopping of motion So let's look at some of the bigger ones. We can't analyze all of these because that will be very much into material side domain. We are not going to analyze. Very soon we will see how we can convert all of these mechanical properties into an electrical circuit to measure it. Because I'm not going to analyze the individual damping performance, but I just now saw this relationship where damping due to each one of these components, this looks like a parallel combination of capacitors, right? Or is it, a series combination of capacitors or a parallel combination of resistors, right? Yes, no? If we have resistors in parallel, this is how we add them, or we have capacitance in series. So this is already giving me an idea. Rather than designing mechanical system as mechanical systems, what if I transform their property into equivalent electrical property and design the whole system as an electrical system? There are few advantages of doing this. We know how to simulate an electrical system. You are working on cadence, we have got SPICE, we know KCL, KVL. They are comparatively easier than to analyze each one of these individually. Anyway, let's look at the big damping things which are there for us. One is fluid damping. Now, almost all resonators on earth are moving in fluids of some sort or the other. Air is also a fluid, right? So either we are moving in air or we are moving in a liquid medium. And here, my surface interacts with the fluid, and my fluid is stopping my surface from moving. Okay. Now, the effect of this damping, the fluid damping, is generally proportional to the velocity, not acceleration. The faster I move, more I am being damped. Car scenario again. Once the car has been started, the road friction is very low. Right? You only need to put gas to increase the speed. Actually, you still need to put gas even to go at a constant speed. Do you do? Or else the question lies, if you need energy for acceleration, you need to apply a force for acceleration, right? Force is equal to ma, not for maintaining a velocity. But in cars, even to maintain a velocity, you still need to give fuel to it, or else it dies on its own right. Now, the quickest way to solve air-based fluid damping is actually to take these sensors into low pressure. So you can put them in low pressure chambers, reduce the atmospheric pressure, there is less air there, there will be less damping. So number of experiments which we have done in past, including those resonators which I showed you, were done in a kind of a vacuum chamber, not pure zero vacuum, but somewhere where the air pressure has been reduced significantly. And there lies the immediate concern with these devices. The devices work brilliantly, but if they're only going to work in low pressure, they will not be very useful for real life experimentation. Now, but anyway, you can still say, okay, we do the experiment, the relationship there, and then bring it down to low pressure to measure it. So till a critical pressure level, low air pressure leads to low damping. After a certain pressure, the fluid damping is independent. It doesn't depend on this at all. Then there is a squeeze film damping. Now remember, we are making our resonator on a substrate. So essentially, I would have made it something like this. There is a structure which has allowed it to move. So I would have removed everything from here, hold it there, and then allowed it to move this way. Or it is held like this and I'm asking it to move there. So in between my resonator and the substrate, there is a thin film of fluid, air. Now that's the air which is very difficult to remove, even when I'm taking it down at low pressure. And it leads to damping, it leads to stiffening of the structure. The structure doesn't like moving. And it's affected by a number of factors, things like what's the size, how much is this structure, how much is the gap between my substrate and the resonator. If I have bigger gap, that will be low because squeeze film damping will not be there. What's the thickness of the fluid, how much radiation we are going. Okay. Then we have structural damping. The structural damping happens is the second order damping relationship. So as my things move, they cause stress and strain in different parts of my resonator, which then leads to heating there. Heat is a loss mechanism. Energy is being lost if something is being heated. At the same time, there might be some places which will be cold compared to this. So there's cooling taking place, which is also a loss mechanism for it. So once I have got a hot structure on one part of my resonator and a cold structure on one part, I've got a heat current flowing between these two. It looks like a potential difference. Okay? So there again, I've got a new damping mechanism. Then our clamping and anchor damping, I'm clamping my structure to something so that it can move. It's not a freely moving structure which is moving. It's held from one side, either on this or on both sides. There is an elastic wave moving in my resonator which sees a boundary here on the clamps. It cannot move beyond the clamps. So this looks like a we have in communication waves, we have got signals bounces out, the reflection of the signal. So that leads to structural damping. Then you have got material damping. Ideally speaking, we would have made our resonator perfectly from the same material with no air gaps. It will be a smooth structure, but we know structures won't be smooth. There will be some rigid structure. And this would lead to damping on its own. Now, this is the most difficult damping to model. Okay. It can be limited by processing steps. You can heat the structure, make it as smooth as possible. But at the end of the day, it is still fairly difficult to model. It depends on the operating temperature a wee bit, but just a little bit on that. So what we have seen is we can make a moving structure, but it causes quite a lot of issues in damping, and I learned it the very hard way. So remember, I made those resonators. The resonators were made to measure very tiny mass, and we could measure very tiny mass. So on the things were moving, we could deposit a small amount of platinum on them and then measure the exact amount of platinum but just by looking at the frequency shift, and the device worked brilliantly. Then we thought, oh, that works brilliant. Why can't we use it as a biosensor? Remember, we did the biosensor calculation. So I took my resonator to a colleague in Ireland, And they said, but our solution is in liquid. We have got this mRNA or bacterial solution in liquid. And so we coated our sensor with some reagent, and the idea which I thought was, okay, we take my resonator in the liquid, let the reaction take place, let its mass change. I will bring it back. I'll put it back in the vacuum and measure its frequency change. So I measure the frequency of resonator, resonant frequency, take it out of vacuum chamber, let it react, bring it back to vacuum chamber, and I will be happy, done. The resonator never worked after taking it into liquid. We tried everything, applying high force. The classic way to move my resonator was to poke it with a hair. Remember, this is 100 micron big. So our hair is 100 micrometer thick. So I used to go about either plucking my own hair or asking people for a sample of their hair to poke it. It will not move. After much effort, what we realized, that there is something called surface tension of water, which we electrical engineers have completely forgotten. Do you remember surface tension? It makes those air bubbles kids play with, right? It forms an air bubble. We never see that in electrical engineering. We had bubbles formed between this structure and the substrate. And now because my structure is very small, the surface tension looks like a very high force. And I could not remove that liquid. Whatever I did, I heated it, I took it to low pressure, that liquid just got stuck there and it will not leave. And this area we're talking about is roughly 100 nanometer thick. That's it. It's a very tiny amount of liquid. But for that resonator, it's a solid resonator, that liquid surface, that bubble had very high force that will not allow it to move at all. So forces which we can ignore at mega scale all of a sudden become very important at micro scale. So far so good. But still, having said that, a number of these devices are being used commercially. We will talk about gyroscopes a bit later, the ones used in cars, how they operate. This is more of a research line direction. The other thing which happens when you make devices very small is they start becoming nonlinear. Our entire electrical engineering theory is based on linear control theory. Agreed? What do we do when things become nonlinear? How do we analyze nonlinearity? So say that's a linear system wherein that was my original resonance frequency, something happened to the system, it moved. But the shift is still a very linear shift. It still looks like a resonant system. What if it starts looking like this? That's not a sinusoidal frequency response of a sinusoidal system. Okay. Or let's take a system like this. Ignore wherever this response comes from. If you ever see a response like this, what do you do? And you have seen a response like this in transistor responses. So how do we analyze this as electrical engineers? We do one of these two things. We either say, okay, sir, this is nonlinear, but if I only operate it till this point, it looks like linear. So we'll only operate it in the lower region. There it's linear. Or we say, okay, it's linear till here, from here to here it's linear, and from here to here it's linear. So we do piecewise linear approximation. Okay? Now piecewise linear approximation works brilliantly, but then you lose all the good things which you get from nonlinear dynamics. Nonlinear systems by themselves have got very beautiful properties. So let's look at one of these properties. And we can do maths very easily. So remember how we analyzed pendulum in our high school days. Remember, you did the pendulum experiment in your school, right? Or have you seen a pendulum in your life? Move it on one side and it keeps on rotating. Okay? So let's remember the high school maths of that time for a minute. So what did we do? We said we move it up What's the force acting here? So this force is tension T. This force will become T cos theta, if this is theta. And the restoring force which is trying to bring it back will be T sin theta. Agreed? And then we did this wonderful thing of maths. We said if theta is small, sin theta is same as theta. Right? That's the Taylor series expansion. The first term is theta. What's the full Taylor series expansion of that? We have got theta minus theta cube by factorial 3 plus theta 5 to the power factorial 5 and so on and so forth. We said if theta is small, you can ignore all the higher order terms. What if theta is not small? Or what if my pendulum is too small for theta to be ignorable? If my pendulum is just this, no, just this much. At this point, this looks like a big angle, isn't it? So my standard equation, if you remember, came something like, we had an equation like this. This was a second order differential equation. It's the same as the mass spring equation which we get, which is mx double dot plus bx dot plus kx is equal to the applied force. And this linear function came because we had assumed this theta to be. So let's take the first order nonlinearity, theta cube. Okay. Again, from mass spring system, we generally take the cubic form because the square law force, what do we say? Force is equal to minus kx. Okay? Actually, force is equal to k times minus x because we are moving in the opposite direction to the force. So if we had a square law nonlinearity, or second nonlinearity, then the force would have been k minus x, that's the linear force, plus some k2 minus x square. Minus x square becomes plus. So if we had the square law nonlinearity, which we do sometimes, but for the first order mathematical operation, it looks like I'm pushing the beam on my side and there's more force taking it further on this side, which is a bit counter to nature. Nature should try to restore. Right? If I'm pushing it, if it goes on there, then it becomes cylinder. So the first force we see is the cubic. Cubic is in the same direction. Minus x cubed is minus. So we now get a relationship something like this. Plus kx plus k1x cube is equal to some sinusoidal force. What will be the solution to this? So that part you can solve. Every maths course teaches you how to solve a second order differential equation. All I have done is I have added a simple nonlinearity to it. Just one cubic term, nothing else. I haven't done anything to the damping yet. Okay? How will you go about solving this? Now here's a fun part. Most nonlinear dynamics equations are unsolved. There is no closed form solution to this problem. What you can do is you can do perturbation and find an approximate solution. You can write a MATLAB code or a Python code to time series simulate it by using Newton-Raphson method. You cannot find analytical solution. So this problem was studied first by Duffing, a German mechanical engineer. And he looked at how mechanical structures move when they have got nonlinearity in their spring constant. There could also be a nonlinearity in this term, the damping. Damping is linear here, it's directly proportional to velocity. Right? We could get a cubic order nonlinearity as well, or we could get more written as something like this. Because if you have an x dot cube and you are doing dx by dt, this looks like an x square dx by dt, right? X cubed dx. So we get a relationship like this where you have got an x square x dot term and x term by itself. This kind of nonlinearity was studied by an electrical engineer for the first time by the name van der Pol in light bulbs. And these two gave birth to the field of nonlinear dynamics. The entire field of nonlinear dynamics, which is studied quite a lot by physicists and mathematicians, rose out of work of our field, and we have forgotten all of it. We don't study light bulbs anymore, right? We don't, the vacuum triodes, we don't study, right? But these are very interesting equations. Duffing and the van der Pol. Van der Pol is a very interesting equation because van der Pol can make an oscillator. So a classic oscillator, a bit diverging from the topic, but I really like this thing because I had to learn this as part of my postdoctoral. We never taught nonlinear oscillators in our undergraduate or even in graduate studies. We only taught linear oscillators. So linear oscillators produce this as a response, a sinusoidal response. Okay? If you have a nonlinear oscillator, you might get something like this. It looks like the RC charging, rapid discharging. You could get, so depending upon the initial condition or the excitation voltage, the same nonlinear oscillator will give you a different response. Now, this is written in the literature, but it so happened my wife noticed it in one of my research papers, and that's how I got even more excited by this. My wife is a medical doctor. She has, well, I shouldn't say she has no knowledge of maths, but generally they are don't have a love affair of mathematics as we do, right? And she saw similar relationships, actually basically doing this and then quick discharge, rapid discharge. And so like that's the waveform we look of human heart, because that's how the human heart goes. And then I would, yes, van der Pol oscillators are used to model the human heart. And this very simple relationship, wherein you just bring nonlinearity to the damping term, models a large number of things in nature. How do we walk? Quick, start, charge, start, discharge. So our walking motion is an oscillatory motion, but it's not a linear oscillator. It's a van der Pol oscillator, with a slight nonlinear. How do fishes swim? Charge, discharge, charge, discharge. They are oscillatory motions, aren't they? Now, funny thing is this. The reason why I'm talking about nonlinear oscillators, look, nature made good use of nonlinear motion. Heck, we walk using that. Our heart behaves that way. And we are saying, we do a piecewise linear approximation of this because we know linear control theory. We don't understand nonlinear control theory there. Okay? So there is a rich amount of literature on nonlinear control systems which can be used for sensing purposes. I mean, think of it this way. That is the response of a Duffing resonator. If I put kx dot, what happens is so in a linear resonator, we go up and we go down in the same way near the resonance frequency. A Duffing resonator, it goes up, saturates, and then has a rapid fall. So if you are thinking enough, you might think of well, we could make a resonator, or we make a sensor where when you're operating here, and if anything changes, the response immediately falls down. That's a highly sensitive sensor, if we could control the nonlinearity. Okay? So if we get time, I will talk more about nonlinear systems. They are very rich, very dense, and quite frankly, I've spent about last 6 or 7 years trying to understand them. I only understand a little bit. We have published some decent papers on it, but we only understand a little bit on this thing. So that is what I was working on, looking at the nonlinear relationship of the pendulum. So pendulum moved further also behaves like a nonlinear system. This is the Duffing nonlinearity. This looks like, so it could be positive or negative. And in real world, it looks like my spring has hardened. So a linear spring will have the same force as you push further. A hardened spring, you push farther, it will try to pull it back. Or a soft spring will allow you to pull further back. So nonlinearity here is looking like my spring is a hardened spring or a softened spring. And this shows something interesting. We have got this hysteresis kind of response. So a simple resonator will behave classically in this form, wherein you have got a symmetric response in the frequency domain. A hardened duffing will be bending on one side, and it will also show hysteresis in the sense if you are going from positive to negative, you will follow this path and then fall down here immediately to come here. And if you are going from high frequency to low frequency, you will not go up immediately here, aka, so here you would go here and then drop here. But if you are coming backwards, it will not go up here, it will go up till here, then move up and then go down. And the same relationship is seen in the softening response as well. Okay. Similarly, as I said, you could have nonlinearity in damping, and that would lead to a van der Pol type of relationship. Despite 100 years of nonlinearity work, we are still barely understanding nonlinear system. So both of these systems can go chaotic. What's a chaotic system? How do we mathematically define a system to be chaotic? You have heard the word chaos. We always have chaos in our society, right? But what is a chaotic system? So a chaotic system is defined as a system which, for a very little change in the initial condition, leads to a big change in the final condition. Okay? So mathematically, universe could be a chaotic system. Had the Big Bang happened slightly differently, we might be completely different. Okay. Weather pattern is often called a kind of chaotic system. You've heard about this butterfly in China theory, that if there's a butterfly flappers its wing in China, that might lead to a hurricane somewhere, because one thing is related to another thing and so on and so forth. Both of these systems can be built into a chaotic system. You excite them with enough force, they will lead to a different response in different excitation. Good. So we have talked about single structures. We have talked about nonlinearity in the structures. We have talked about different type of excitation and measurement. Remember, I'm not going deeper in any one of these because I'm giving you a broad overview of the whole thing. One last thing which I would like to talk about, and let's see if we have enough time for it, because I might have to go and say hello to someone, would be coupling. Oh yes, we have enough time. So till now we were looking at one resonator. Each resonator is a few micron. Why make just one resonator? Why not make more than one? We make more than one transistor on a chip. Now that's one of the reasons why we have been successful in the electronics world. We can make a billion transistor on a chip. The microelectromechanical system world is still very much stuck at one or few sensors per chip. You may make only one gyroscope on a system. This is where I also spend a lot of time working on our research, wherein we generally don't like mechanical coupling because our system is moving nicely. There's another system which starts moving on this side. It will couple its response to this, and my movement won't be nice anymore. So generally speaking, we don't want any coupling. We want our system to be pure in its own environment. A very good example, have you guys done double pendulum experiment in your school? You take two pendulums, connect them with a spring, what happens? Never done experiments like these? You know what? Let's make a double pendulum in the afternoon. Okay? What do I need? tennis balls. Anyone has spare tennis balls to give us? Don't worry, I'll go and buy the double pendulums because they are very nice experiments. So, if you take two pendulums and connect them with a string, there's only two ways the pendulums will move, whatever you do. They will either go together or they will go in opposite direction. You excite them here, you bring them here, leave them after a few minutes, that's the natural motion they will come in, as long as they are linear systems. Okay? You take three pendulums, there are only three ways they will move. Either all three will go in the same direction, or the middle one will remain fixed and the other two will go up and down, or the other two will go in the same direction, but the middle one will go to square root 2 times more in the opposite direction. Now, these motions are fixed by a very decent maths we teach to all our students. Remember eigenvalue and eigenvector. We take matrices, we take eigenvalues, we take eigenvectors. So, if you consider two pendulum, it looks like a 2 by 2 matrix of a system. Okay? It will have two eigenvalues. The two eigenvalues are its two resonance frequencies. It has two resonance frequencies, one in motion and one out of motion. And the amount by which it moves by, that is its eigenvector. Okay? It took me 6 months to figure this out. Once again, we have done eigenvector and eigenvalue, but quite often we do not correlate it with something in mechanical engineers do it. We unfortunately don't do this thing. So, I will just do analysis of one system to show you why it is interesting. So, remember those big resonators I was making? We actually made 5 of them coupled with one another. So, essentially what I wanted to see is I know this motion happens if I take two pendulums and I just move one pendulum, in due course of the time the other one also starts moving. If I move one, it will move and it will slowly make the other one also move, and in the end they both will move either in phase or they will move out of phase. Can I use the same logic to make an array of sensors where I just have to excite the first one? Otherwise, if I make sensors, I need to excite each sensor, I need to measure from each sensor. But I know from this pendulum thingy that I can excite all of them. So, can I make an array of sensors, just excite the first sensor and hope all of them start moving? The other thing which we know is the frequency at which they move is the eigenvalue of the system. If any one of my resonator changes, think of a matrix, right? If you have a 5 by 5 matrix with elements only on the diagonal or an off diagonal. If any one value changes, my eigenvalue changes, right? Now, my eigenvalue is the resonance frequency of the system, which I can measure from the response of any one resonator. Think again, two pendulums. Actually, you know what? Do I have a theory of two pendulum? Yeah, I've got two pendulums here. So, these are two mass spring systems, okay? Two mass spring system, and I have coupled them with another spring. So, in the end what they will do? They will either go this or they will move together. So, if you now look at their frequency plot, we will have two resonance frequencies, one in which they are moving in plane, they are moving together, and one in which they are moving out of plane. And both resonators will have, the frequency will remain the same at which they move in or out. The amplitude might be different depending upon what's the individual sizes of the resonator. Their frequencies will always be the same. Okay. Now, if something happens, let's say my resonator 1 has changed. Okay. You can see the resonance frequency shifts. So, blue is my original response and red is my shifted response. The same thing happens when resonator 2 changes. So, essentially if I have an array of resonators, I can measure the entire resonance frequency from the response of the first resonator. Then if my fifth resonator changes by measuring mass or stiffness or something, the entire eigenvalue of the system will change, which I can still measure from the response of the first resonator. So I can have an array of sensors and just measure it by the response of one resonant system. And I will show it to you here. This is a 5 resonator system. That the solid lines are the frequency response to various frequencies. You can see it's in kilohertz, but nothing has changed. That's its natural response. At one frequency it has got low amplitude, at this frequency it is high, so on and so forth. Now I go and change the third resonator. Oopsie daisy. I think that is telling stop talking. It's lunch hour now. Is it lunch hour? Almost? No? Let's carry on till Professor Muralidhar comes in and drags me away. Is he already there? No. So when we change the third resonator by putting a small mass on it, and we are still measuring only the first resonator, we are not measuring the third one at all. The frequency response of the entire system shifted. This one did not shift by much. This one shifted by a large amount. This one shifted here. This one shifted here. This one shifted here. Okay. So just by looking at the frequency response of the first resonator, I can tell which one of these resonators have shifted. We also did this experiment with this coupled system. We have got 5 resonant systems, and at this point what we did was, as you can see, we have cut one of these slightly. Okay? And once again we saw a change. If you can see the dashed line, we saw a shift in resonance frequency response from one resonator system. So this kinda allows us to make a mechanical multiplexer. What does a multiplexer do? It selects one of many. Now we can measure the response of an array of the system just by looking at response of one system. Now how do we do maths of this thing? So let's see what's going on in the mathematical part. If I write the equation of the first mass, I have got mx1 double dot plus kx1 plus, so kx1 is its own spring constant, plus then there is a k coupling, which is the middle spring. K couple, and that spring sees the motion which is difference between the x1 and x2. Still a linear system, okay? So x1 and x2. The second one has similar equations, but now it has got a coupling which is x2 minus x1. It sees the other relationship. Okay? If I write this as a matrix form, I can write a mass matrix M where just M1 and M2 on the diagonal. There is nothing on the off diagonal term. And I can write K as a stiffness matrix. So the stiffness matrix will be of this type. So what's related to x1 in the first equation? I just have k plus kc. Related to x2 in the first equation is just minus kc. Related to x1 in the first equation is kc plus kc. If you expand this term, think of expanding this matrix, The first line of this will be m1 times x1 double dot plus 0 times x2 double dot. This side plus kc times x1 minus kc times x2. That's my first equation. The second equation similarly is m2 times x2 double dot plus minus kc times x1 plus kc x2. So this matrix represents that equation. Okay? Now, if you remember, that equation looks like the starting situation of the eigenvalue relationship which we teach to our students, right? And I can write this as, you can take m as m half, or even if you can normalize the whole m to become 1. We can take all masses to be 1. This becomes the eigenvalue relationship. It's the eigenvalue of this matrix which then tells me at what frequency my system will move, and the eigenvector which tells me how much they will move by. Okay? If I extend this relationship to n such systems, then I will have a tridiagonal matrix where all other terms are 0. Remember, because this element is only talking to its nearest neighbor. So if I have got a second element, it has got some response from the first element, is doing something to the second element. So I will get a large matrix which will be a tridiagonal matrix, and the response function of that tridiagonal matrix will give me the eigenvalue and eigenvector of these systems. So here is what my 5-element system behaves like. Remember, I made, okay, right now I'm showing you just 3 for the shortage of space. But we made 5 such resonator system, and we measure the response function. So on the solid lines, we have got the amplitude response. On the dashed lines, we have got the phase response. And as I said earlier, it can act as very good mass sensor for very small masses, as well as a very good stiffness sensor for very small stiffness changes. I will leave you shortly, because the question here again is, MEMS world has always lived in future. They're always talking of new materials, new type of designing circuits. Each physicist and chemist has his or her own favorite material and favorite design. What people don't talk much about are how to design, what's the noise, what's the variability, what's the nonlinearity in the system. And this is where we as electrical engineers can contribute to this field from a research point of view as well. We don't want to change the material. We don't want to change the design. We want to have one standard. Remember what I did just now. I picked one design of resonator, and I said I will just make loads of copies of these and then see that as, because that way